Yeah, as Julia mentioned, my name is Arthur Davis, and I direct our community scale urine recycling program here at Rich Earth, and participate in a lot of the physical research that we do here. And I'll be introducing everybody for this session. So our first presenter is going to be Kai Udert. The title of his presentation is State-of-the-Art Urine Treatment Technologies. And Kai Udert is with the engineering department at AVOG and has been working on nutrient recovery from urine for most of his career. His research is guided by the principles that human waste must be seen as a resource to replenish nutrients for food production and to prevent environmental pollution due to uncontrolled discharge. So welcome, Kai, and you want to share your screen and take us away. Thanks so much.
Yeah, so I actually believe in urine to be a resource, and I'm not the first one to do that. There have a lot of people there been before, as you see here, Henning Brandt. He's a guy from Hamburg. He really believed in urine being a rich resource, and he did a lot of experiments, a lot of treatment with urine in the years 1669. And this is not really the current state of urine treatment technologies, but I will get back to that. Okay, what do I want to talk about? It's in 2006, there was a first paper from my colleagues here at AVOG on treatment processes for source-separated urine, 2006. There were only very few urine treatment technologies which have already been tested. And there have been a lot of suggestions what kind of processes actually could be used to treat urine. And we think now that's about 15 years ago, we thought actually it's about time to look at the literature, what happened in this 15 years, and actually quite a lot happened. And we are convinced that this will be the last time that we will do this review paper because there's so many processes around and it's just growing and growing, and it will be really hard to write such a review paper, at least for us in the future. Now, this paper here, you see it on the right side. The main author is Tove, and also Michel was part of the team, Michel Riechmann. We looked at the papers that we found from 2006 until 2019. It's all the scientific literature, so a lot of the experiments which have been done by other people, in practice, they're actually not covered in here. But we actually found reports about lab studies, pilot studies, and also a few processes which are really close to market. So, but there are only very, very few processes which are close to market. And actually there's no process which is already on the market, at least until 2019. Now, what are the treatment goals? So you can summarize it here. A lot of the research actually focuses on recovering single nutrients. So the most important ones are nitrogen, phosphorus, and potassium. Precipitation processes, especially, but also absorption. There are some processes that actually focus on water removal, so getting the water out of the urine, and by this actually concentrating the remaining ingredients. Then stabilization is a really important. What do we mean by stabilization? One factor might be a removal of the COD. So the COD, that's a measure for the organic content in urine. And this also means we want to remove the malodor, the bad smell from urine, and also the organic materials which could serve as a substrate for bacteria. And also we want to make sure that ammonia actually doesn't volatilize, because this is one of the major issues when you use stored urine, for example, directly as fertilizer. Nitrogen removal, that's another process which has been investigated. So really, collect the urine, it's the main nitrogen source of wastewater, and by targeting the nitrogen and removing it, for example, by electrolysis or nitritation anammox, you could solve at least the environmental issue, and that's the pollution with nitrogen. There are also studies on energy production and risk mitigation as well, pathogen removal and micropollutant removal. But what we did not find was actually the production of gold from urine, and that actually was what Henning Brandt was looking for, here in his lab, his alchemist lab in Hamburg. He actually tried to find gold. What he found was phosphorus, and that's actually this really bright light that he saw here, and was totally surprised by that. But there are still a lot of people who would call gold, urine the liquid gold, and I think in some respects, this might be also true. Okay, let's move back from alchemy to reality, today's reality. What were the processes that we found? So long list. So those are the processes that we found: biological processes, physical processes, chemical processes, and I will not discuss all of those processes. So I just want to give some highlights. And the first highlight, actually, it's the electrochemical processes there in the right corner. The fuel cells, microbial fuel cells, electrolysis, microbial electrolysis cells, electrodialysis. So these 5 electrochemical processes were completely new. So they were missing actually in the first review in 2006. And there were, I think, close to 100 papers on electrochemical urine treatment. So, and the reason for that is also because urine is a really good material or liquid to be used in electrochemical processes because it has a high conductivity. And it also has a lot of reduced compounds like organic compounds and nitrogen compounds, which can be oxidized on the anode. Now, what could be the purpose of electrochemical processes for urine treatment? So one goal, and I think this was one of the main goals in many studies, was the power production. So to get electricity out of urine. And there are basically 2 processes. One is a fuel cell. The other one is a microbial fuel cell. And with a fuel cell, so that's purely chemical, no bacteria involved. The target or the reductant would be urea. It could also be ammonia, but what we found in literature was urea. And based on the literature data that we found, this paper by Lan and Tao, 2011, we could calculate the power production. There was about 0.78 watt per person. So that's the power that you get out of urine. Microbial fuel cell, there has been a lot of research on that. And the reductant, the source of energy for microbial fuel cells, those are organic compounds, especially acetate, so COD. And for this, based on literature, we calculated the power production of 0.22 watt per person. So is this a lot? So for comparison, the average electric power consumption in Switzerland in 2019 was 760 watt per person. So it's 1,000 times more, or even more when it comes to microbial fuel cells. So just by electrochemically treating urine, we will definitely not solve the restrictions for electricity that we might have in our countries. So this is, I think, important take-home message, but there might be other advantages of electrochemical urine treatment. For example, nitrogen removal. So here we see 3 processes: electrolysis, direct ammonia oxidation, which is also electrolysis process, and fuel cells. So what's the difference between electrolysis and fuel cells? Electrolysis, we have to apply a power, while for fuel cells, the anode reaction actually produces power. And there we actually see it's a minus 1.8 kilowatt hours per kilogram nitrogen. So the fuel cells actually produce energy. But what's important, what I want to point out, that with electrolysis, we can have extremely high degradation rates. So in this study by Zöllig, the degradation rates were up to 420 gram nitrogen per square meter a day. And this is something which is so much higher than what we actually find in biological systems like denitrifying biofilm systems. But it comes with a disadvantage. And this disadvantage actually is the production of chlorination byproducts. So the reactant which is actually produced, so the reactant that actually oxidizes the ammonia or the urea, that's chlorine. And chlorine will also react with organic compounds. And so we get a lot of chlorinated byproducts, which are really unhealthy. One example is chloroform, but there are many more. And they're most often also volatile. How can we solve this problem? So we could have direct ammonia oxidation. So this is a process where we don't apply really high anode potentials, rather lower anode potentials. So we don't have the chloride oxidation to chlorine, but also then actually the degradation rate will decrease as well. We see it here, it's 2.9. So that's actually in the same range as denitrifying biofilm systems. But still, I think when it comes to nitrogen removal, there is some potential when we see for electrochemical treatment. Now, COD removal. we can remove nitrogen compounds. We can also remove COD compounds. Again, electrolysis up to 421 grams COD per square meter a day. And again, we have the production of chemical chlorination byproducts. The solution might be a microbial fuel cell. I presented that before. Microbial fuel cells are usually applied to gain energy, so electricity, but they could also be just used to degrade the organics. And here we are in a similar range with the degradation rate as conventional biofilm systems. So again, electrochemical systems for urine treatment. Our conclusion was electricity production, no, this is probably not the goal, but for the degradation of nitrogen or COD compounds, it might still be interesting. So this is a really short summary about this new category of processes. Now, when we look at all the processes that we investigated here, actually it's a summary, it's actually the graphical abstract of the paper, and we only see some examples of processes. And on the y-axis here, we see the technology readiness, and here the different treatment technologies, and we see the ozonation, also phosphate precipitation, and then nitrification distillation and alkaline dehydration. And those two processes, so the combination of nitrification distillation and the alkaline dehydration, there we would assume they have the highest technology readiness. So Fabien presented actually the process nitrification distillation very quickly. It might be one of the processes to be implemented in Paris, and also alkaline dehydration. There are at least two types of reactors available or being developed, and it's already really far into commercialization. Just some quick words about it. Nitrification here, it's a biological process where ammonia is converted to ammonium nitrate. So it's actually the stabilization, COD is removed, and ammonia volatilization is prevented. And then in the distillation step, actually the water is removed and pathogens are killed. In the alkaline dehydration, calcium hydroxide, another base is added. And by adding this base, urea, hydrolysis is prevented, also the fermentation of organic compounds. And later there's heat or just a lot of ambient air being used to remove the water. Now, when we look at those two processes, which we assess to be the processes the closest to commercialization, we see a big difference. One is nitrification distillation. This is definitely a process rather suited for large buildings. So what you see here is actually the EAVAC main building, because the biological step needs really robust process control. And this is something which might not be achievable in a household, in one single house. While the alkaline dehydration could be used for single toilets. And what you see here on the right side, that's actually a pilot study in Durban where alkaline dehydration was actually used. Now, one more point, what are the main challenges for technologies and where do we see the most need for further development? And that's actually the removal of pharmaceuticals and pathogens. And this also comes from the fact that when we think about using the products from urine treatment in agriculture or horticulture, somewhere else, we have to make sure that there are no pathogens in there and also that there are no pharmaceuticals, because this is, at least to our experience, those are critical factors for the population. I think we heard it before, but also for like agriculture ministries and so on to give a license to those fertilizers. And actually, I want to refer to two documents here. One is a German standard, DIN spec. It's still a private standard, not the official DIN standard. But this standard was actually developed according to the DIN rules. And it's the quality assurance of recycling products from dry toilets for use in horticulture. So actually this standard, it's a German standard, but actually English translation is available. And this was actually, we tried to find quality rules or quality assessment guidelines for such recycling products, because we think that this will be crucial to really find the acceptance on a larger market. And one excerpt actually from this standard work is this paper here, the qualitative risk analysis for contents from dry toilets. Okay, so with this, I already come to the end of my presentation. Again, I think when we look at urine treatment processes in the beginning, there was still a lot of focus on recovering single resources that might be nitrogen, phosphorus, gold, 400 years ago, or maybe just removing nitrogen. I think today the focus, also when we looked into literature, is really recovering most of the, or even all of the nutrients, and trying to contribute to closing the cycle between cities, here, agriculture, and production. Okay, with this, I want to close here, and I'm looking forward to your questions.
Thank you so much, Kai. It's really so valuable to have such a conglomeration of all of the research that's been done in the previous decades. So thank you so much for your work. Moving on, again, we'll do the same thing. So if you have a question for Kai, put it in the chat and we'll come back to all the questions at the end. Our next presenter is Michel Riechmann. And his presentation is called Field Testing the Blue Diversion Autarky Urine Treatment. And Michel Riechmann worked on several different toilet projects in Germany, Mongolia, and South Africa. Since 2017, he dedicates his research to resource recovery from urine at the Swiss Aquatic Research Institute, EWAG, working on the development of the Blue Diversion Autarky toilet system. Besides that, he is involved in technical working groups for resource-oriented sanitation in Germany, Switzerland, and the US. So thank you so much for being here. And if you can share your screen and go for it.
Okay, let me share my screen with you, and there we go, and I start the presentation. Now, is it the right one you see?
Yes, we
Yes,
see
okay.
Your presentation.
It's only the last slide.
That's good.
There we go.
There we are.
There we go. Okay, thank you very much. I have to say hello as well again. I hope everybody is enjoying the summit so far as well as I do. I will now present a little bit, you said it before, about the field tests we did on the Autarky urine treatment. And first of all, I would like to tell you a little bit in general about the toilet system we developed. Our aim at the beginning, when we started the project of the Blue Diversion Autarky toilet, was to design a toilet that is affordable and dignifying for all people who use it. And we amplified a 10-person's household to be our treatment goal, and had the idea that all waste streams should be treated on site. We choose source separation as the right approach to it, and as you can see on the left side, we have 4 different treatment modules that can be used as a whole or individually for treatment purposes. Now, I will now focus on the urine treatment, and you see the module on the right side, and I will go a little bit closer into the treatment process. Well, first of all, the specialty is that we use fresh urine and not stored urine as many other treatment processes. So we collect with either flush toilets or waterless toilets. Then we have a 2-step process where we have a stabilization reactor at first place and an evaporation unit subsequently. Now, how do these work in detail? As you might know, fresh urine comes with nitrogen present as urea, but this quickly degrades to ammonia. So our first goal is to stabilize the urine, and we do this by using calcium hydroxide. calcium hydroxide is a cheap reagent, which you can get in almost every hardware store. And what it does is that it elevates the pH of the solution to above 11. And at this pH, urea hydrolysis is suppressed and pathogens are killed off. Another side effect of the dosage of calcium hydroxide is that the calcium, the phosphate precipitates together with the calcium and forms a first product. Well, after the first stabilization step, the urine overflows to a stacked tray system and the evaporation unit. And throughout the unit, we have a system of stacked trays to create a large surface area. We have about 6 square meters where we distribute the urine on a natural basis, meaning there's no pumping involved, so all natural overflows. And what we do is we blow ambient air, there's no heating over the trays, and evaporate and concentrate the final product. Like this, we have our second product, a nutrient-rich multi-product of nitrogen, potassium, and sulfur, and all minor nutrients. Now, as many of you may know, there's always the shiny lab studies where everything works fine and everything looks beautiful, but then there's real life. And we also got to this point where we had to field test our system. And I will show you the results now of these field tests. And we had the following aims before we went there. First was to have sufficient water removal. Then we had the ambitious goal of recovering all nutrients present in the urine. Then we wanted to produce a high fertilizer, a high quality fertilizer. And in the end, do all this by having a very low energy demand. How did it look like? So we went into several field tests. The first was at ERWAG campus here in Dübendorf in Switzerland. The second was attached to a tiny house in Au, also in Switzerland. And the last was in Durban in South Africa, where we cooperated with a 14 people household. Now, I cannot, due to time constraints, show the results of all, so I will just focus on the ERWAG field test. And we start off with the water removal. So as you can see, we had a quite good removal efficiency of 96%. Although throughout the test, the reactor was on average just used for 50%, meaning that we couldn't produce enough urine to reach the limit of the reactor. What we also found is there's a very strong dependence on climate conditions. Relative humidity and temperature drive the evaporation rate directly, meaning at a high relative humidity, you can directly see a lower evaporation rate. And this is also the first thing we saw in difference to the lab studies, as lab studies always are made like inside the building, and these tests were then moved to outside. There's very different climate conditions, as inside a building there's very constant temperature and relative humidity on a low level. Outside the fluctuations are very high, and in generally the relative humidities are much higher than inside. Coming to nutrient recovery, we were very satisfied when we had our first tests, and these were batch tests for 3 days already with the evaporation module, and we found, wow, we have 98% recovery efficiency for nitrogen. That's almost perfect. And then we went to the field, and boom, we had about 75% loss of nitrogen. So what happened here? As we have a very high airflow, this also comes with a high inflow of CO2. and CO2 dissolutes into the urine. As we have a high surface area as well, it goes even faster, and there's a big contact area. Now CO2 in the solution acidifies the urine, the pH drops, and subsequently urea hydrolysis happens again because it's not suppressed anymore. And again, due to ammonia production, acidification is even more enforced. But we are working on this, and there are about 2 measures that we're focusing on to tackle these problems. The first measure is to allow more calcium hydroxide to migrate from the first to the second reactor, and thus have a buffer, a higher buffer capacity for the inflowing calcium hydroxide. The second measure is to reduce the calcium, the CO2. Now, as you might also know, it's a different game always to the other nutrients. Phosphorus, it's fairly easy to recover, and we can recover up to 100% in our reactor. And what we can see here, most of the phosphorus goes to the first product, as I showed at the beginning before. About 90% go to the calcium phosphorus product, and only a very small part goes to the full nutrient product from the evaporation reactor. Slightly different, the potassium recovery, also full recovery, but everything goes into the second product, the complete full nutrient product from the evaporation reactor. Now, some colleagues of us did some studies on the effectiveness of different organic fertilizers. And as you can see on the very right side, there's a reference fertilizer, water soluble phosphorus. And according to this, the other fertilizers are grouped in this graph. And you can see in yellow, these are 2 of our products. The first UCP is the phosphorus calcium product, and then the UCFN is a phosphorus blended full nutrient product. So the evaporation reactor product plus some of the UCP product. In general, as you can see, the fertilizing quality was very high, about 80% of the reference fertilizer was reached, and it ranged among the highest organic fertilizers tested from the whole range. This was all done on alkaline soil. This is even more surprising as we have an alkaline product already. So this is a very good result for us. Just to make the comparison to standard fertilizers, rock phosphorus, for example, or sewage sludge ash, which is used largely right now, on alkaline soil at least, they have below 20% fertilizing effectiveness. Okay, and last but not least, I will tell you a little bit about the energy demand of the system. So the specific energy demand that we need per kilogram water evaporated is 150 watt hours. Now, what does it mean? Just in comparison to another system, another alkaline dehydration system that was instead of a high airflow used heated air. And as you can see on the energy demand, the heating directly reflects on the energy demand. So it's around 20-fold. What you have to say is that, of course, with preheating, you have also a higher effectiveness in evaporation, but it's up to the users in the end if rather a low energy demand or a lower space requirement is favored. And the last is the comparison to a building scale unit that is already commercialized. A distillation unit uses around 110 watt-hours per kilogram water evaporated, and it's visible that the urine module of our project can almost compete with this building scale unit. Okay, to leave you, I want to give you some take-home messages. First of all, we can say we had successful dehydration using just airflow and without additional heating. We have to say we had major nitrogen losses during the long-term tests. However, these can be reduced and tackled by minor reactor modifications. We further had 2 products with a fairly high fertilizing capacity regarding phosphorus. Other nutrients need to be researched still. These were calcium phosphate, a calcium phosphate product and a multi-nutrient product. And to come to the end, we had a very low energy demand, which was satisfying for us. To conclude, I thank you all for listening, and I leave you with some impressions of the reactor. And if you have any further questions, I'd be happy to hear them, or if you want to have more information, just contact me on this address.
Thank you so much, Michel. It's really exciting to hear about. And anyway, I have lots of questions, but I suppose we'll get to those at the end. But super great. Thanks so much. Next, we're going to be hearing from Abe Noe-Hays and Ryan Homeyer. And they're going to be talking about a paper that Rich Earth just published, also with Nancy Love from University of Michigan. It's called Advancing the Design and Operating Conditions for Block Freeze Concentration of Urine-Derived Fertilizer. Abe Noe-Hays is the Rich Earth Institute Research Director, and Ryan Homeyer recently concluded an Eco-AmeriCorps service position at the Rich Earth Institute. Abe will be presenting our findings about a new technology in development for concentrating urine fertilizer. So I'm going to open up Abe's presentation and share my screen and pass it over to Abe.
Terrific. So this is a condensed version of the whole report is in our paper that's in Environmental Science and Technology Engineering, same title as this presentation. And this work has grown out of a multi-year project that started with the collaboration with University of Michigan with Dr. Nancy Love, and now is continuing through the Small Business Innovation Research Project with Rich Earth Tools. As Arthur mentioned, he and Ryan and I at the Rich Earth Institute also worked on this project. So what we were after, oh, and let me also say, I'm going to try to get through this pretty quickly because we are running a bit behind, and we have a lot of people in this session. So I'm going to try to zip through it if I can. Our object in this was to create a concentrated fertilizer from urine. A lot of discussion today about volume reduction or making a fertilizer. We were looking at freeze concentration as a way to reduce the costs of storage and transport and application of urine. And freeze concentration has several reasons to recommend itself. That's a little picture. I'll explain what these parts are later, but that's our actual lab scale freeze concentrator, 2-chamber system, bottom chamber freezing, top chamber melting. The principle with freeze concentration is that as water freezes, as a solution freezes, the ice that forms is pure water, and then all the solutes are concentrated in the unfrozen brine. And as that process moves along and more water freezes, the freezing point of the solution drops as its concentration increases. We chose block freezing as our method because it's a mechanically simple process. There's no agitation, stirring, mixing, transportation of the urine being frozen. It just sits there and freezes in place and then melts. It's physically robust compared to a process like reverse osmosis, for instance, where there's a membrane that can foul. And it's scalable. You can increase or decrease the size of these concentration chambers or have them in series modularly. And it can be quite efficient if the temperatures of the working fluids are kept moderate. So if the freezing and thawing temperatures aren't very far apart, it can be efficient. One other thing is that it works on ammonia, and you cannot evaporatively concentrate ammonia. It's hard to concentrate ammonia with reverse osmosis. We work with stored urine and not stabilized urine. So this is a process that can concentrate ammonia in solution. This is a quick schematic of our setup. It's a side view here. Both this and the previous one are side views. The actual freeze concentrator is a square plate, so we're looking at it on edge. And we freeze from above. This thin plate has a thermal transfer fluid circulating through it that is taking heat out. The ice front forms and it grows through the thickness of that square area that we're seeing in cross section from the side. And when it is mostly frozen, about 80% frozen, we open a valve and begin to drain the unfrozen liquid into these bottles. And it's on a scale, so they're computer controlled to open the valves sequentially and collect fractions. About a 30-hour freezing and melting period on this. And we froze to about -6.5 degrees on our first pass, freezing raw urine into the first level of concentration. And this is what we obtained. These are each the different fractions, 1/10 of the original volume. And you can see above here visually, the first few ones are very dark and concentrated. And this corresponds to this high level of concentration. This was mostly liquid and then a little bit of meltwater. I mentioned that the ice is all pure water, but there are inclusions that are physically held within ice pores. So as the ice begins to melt, some of those inclusions are liberated. And that's why there's some intermediate level of nutrient concentration in the first meltwater. And then the later meltwater has very low levels of concentration. Interestingly, the ratio of nutrients remains constant through these different levels. So there's no partitioning of different nutrients, but there is partitioning of all the nutrients into these early sections. And in order to create a product and to enable further concentration and to minimize loss, we divided these fractions into a concentrate section, which is the product of this stage of freeze concentration, an intermediate recycle fraction that gets sent back into the next stage or the next batch, and then a reject fraction, which is very low in nutrients and can safely be disposed of into a gray water system or otherwise. Now, where these fractions fit in the larger scheme of a multi-level concentration system, we were looking at stage 1 here, and the concentrate from that, the nutrients go into stage 2, become the feedstock to concentrate it further. The intermediate goes back into stage 1 for the next batch, and the dilute effluent leaves the system. So then looking at stage 2, this is the feedstock for stage 2 is the concentrate from stage 1. That has its own concentrate, which is the final product, and then recycles to the first stage, recycles back to the second stage, and there's some that gets rejected out of the system because it's very dilute. And then to put numbers on that, the most relevant things here are the concentration index. CI's concentration index was about a 6x concentration. So we went from the raw urine to the concentrate along these two stages. It was concentrated by a factor of 6. And the reject water had about 10% of the concentration of the influent. So we lost about 10%, a bit less than 10% of the nutrients in the reject water. And those are the most important figures. For time, I'm just going to skip along here and start to talk. There we go. Start to talk about the energy usage. So we are using refrigeration to do this. We're pumping heat, and that takes electricity to accomplish. But fortunately, it doesn't have to take a lot of electricity. This schematic here shows a chamber that's freezing and a chamber that is melting. So the freezing, the coldest we got to in the stage 1 was -6.5, and the ice as it melts is always at 0 Celsius. So this is the temperature differential. And this gray thing represents the heat pump that is pulling heat from the cold chamber into the warmer chamber that we're melting. And we can move a large amount of heat with a small amount of electricity because of, there we go, because of the temperatures involved, because they're not very large in the scheme of things. So between the contents, there's 6.5 degrees of difference. And between the working fluids, the actual thermal transfer fluid that is chilling this side and melting that side, in our experimental system, we had about a 10-degree difference. In the second stage, it's colder because the second stage is more concentrated. The working fluid difference is around 16.5 degrees. So keep those numbers in mind as we go to the next slide and talk about coefficients of performance, basically refrigeration efficiencies. We're talking about a 10 to 15 degree difference in the temperatures of our working fluids, which corresponds to around a 20 to 25 COP, coefficient of performance, meaning for every 1 watt-hour of electricity you use to run the heat pump, you move 20 to 25 watt-hours of heat from one side to the other at this temperature differential. Theoretically, these are the ideal Carnot efficiencies. They translate out in the real world to 50 to 60% of that efficiency, but still, we're talking about moving maybe around 10 watt-hours of heat for every 1 watt of electricity that we invest in the system. And for a comparison, that is, well, I guess I should have put these in the other way around, but what we come out to is around 14 watt-hours of electricity required for every liter of water removed using freeze concentration. And those are the assumptions that it takes 93 watt-hours of heat you have to remove from water to freeze it. That's not really an assumption, that's just a fact. And then the assumption is that we can get around an 8.5 coefficient of performance, which is based on some of the literature around freeze concentration and also based on the temperature differentials that we determined for those 2 stages of freeze concentration in our actual experimental setup. And from our experimental setup, that we had to freeze a kilogram of ice to remove 0.77 kilograms of water because there was some recycling going on. So those are the assumptions. It all calculates out to around 14 watt-hours of electricity per liter of water removed, which compares, it's a little more energy than reverse osmosis, but it's so much more robust and it handles ammonia well. And compared to evaporation, as we were just seeing in the last presentation, around 110 to 150 watt-hours for passive evaporation with ambient air or a lot of heat recovery, or up to 710 watt-hours if you're just using direct electric resistance heating. So it compares favorably to energy demands for evaporation and is comparable to reverse osmosis, which to us is important because we really have an emphasis on not using more resources to create this fertilizer than it's worth, than it would take to manage through other methods. So I won't dwell on these, but the idea that 92% of nutrients are retained, that is a success to us, and that our working temperatures are moderate, that allows us, along with this latent heat recovery of using the existing ice as a heat sink for the ice we're making anew, allows for it to be pretty energy efficient and perform well compared to other options. And then our next steps at Rich Earth Tools is to bring this into a larger scale version that can handle about 1 cubic meter at a time per batch per day. And that could be integrated into this larger system that Kim was talking about yesterday in terms of a building scale treatment system, either for urine, for source separated urine, or for source separated black water that's highly concentrated and digested from vacuum flush toilets. And that concludes my presentation. You can read more details in this paper. If you have trouble finding it or accessing it, please contact me at that address and I can make sure you're able to access that paper. So I think I hit my 10 minutes and thank you very much.
All right, thank you, Abe. Great to hear about. All right. Again, if you have questions for anyone who's presented thus far, put them in the chat, and we will get to them after the next few. So next we'll have Sudeep Popat presenting on stabilization of source-separated urine using electrochemically synthesized hydrogen peroxide. Dr. Sudeep Popat is an assistant professor in the Department of Environmental Engineering and Earth Sciences at Clemson University. Dr. Popat's primary research interests lie in application of anaerobic and electrochemical processes in resource recovery from wastewater. Dr. Popat's current and prior work includes research in the areas of reductive dehalogenation of chlorinated ethenes, anaerobic digestion of municipal sludge, gas phase bioreactors for biological removal of siloxanes, microbial fuel cells, and electrolysis-based processes for resource recovery from wastewater. Dr. Popat's research has resulted in more than 30 peer-reviewed publications. We're excited to hear what you have to present today. So you have the floor.
Great, thank you for that introduction. So I'm going to talk about some of the work that we've been doing on using electrochemical technologies for recovering resources, in this specific case, helping stabilize urine. And so one of the things that we are very interested in, and I think Dr. Udert mentioned it earlier as well, is that there's an interest in using electrochemical technologies in urine treatment. And so one of the things with our microbial fuel cell work that we were able to do was to extend that technology to producing hydrogen peroxide within urine so that we can stabilize it. So before I discuss the technology, I must thank Philipp Markus, who's a PhD student who did most of the work that I'm going to show here today. And also specifically from my group, Emily Murawski, Negin Kananizadeh, and Spencer Lindsay, who moved on to other positions since, but they really helped catalyze this effort by working on the core technology, which is how we produce hydrogen peroxide electrochemically. And a lot of the funding for the work that I'm going to present today came from NASA and the Space Grant Consortium here in South Carolina, with the potential application of using such a technology for space missions. And so a few years back, I toured the urine diverting toilet at University of Michigan, and that sort of inspired me to start thinking about ways in which we could address some of the problems along the urine processing pathway that we could apply some of our technologies to. And so I found out about the Rich Earth Institute then, and I'm going to borrow this from the website, which shows across the entire pathway of how we could go from urine diversion to actually recycling and applying nutrients that are derived from urine. And so a few years back, we started thinking about where we could apply our technologies. And I know one of the biggest issues is how do you collect and transport maybe to a site, and especially the issue with volatilization of ammonia from urine, and that comes from urea hydrolysis, which is a problem. The urease enzyme is ubiquitous and catalyzes the hydrolysis of urea in urine that leads to production of ammonia, volatilization of ammonia, leads to the odor issue with urine, especially during storage. So it makes storage and transport difficult. And some of the chemical signatures of hydrolysis are that you see an increase in ammonia concentration, which is where the odor comes from, but you lose a lot of the nitrogen as well. And so if the idea is that we could recycle some of that nutrient, we lose a lot of that through volatilization. Some of the other sort of hallmarks of urea hydrolysis are that we'll see an increase in conductivity and pH as a result as well. And so the traditional approach to preventing urea hydrolysis is by adding acid or base, which is going to inactivate the urease enzyme, or its activity will be substantially reduced so that you can actually prevent production of ammonia and preserve urea in its original form. So when we first started thinking about potentially addressing this problem, we came across some literature studies that showed that hydrogen peroxide can also be very effective in stabilizing urease. And at the time, we were working on technologies, electrochemical technologies that allow us to produce hydrogen peroxide. And so we were really interested in this, and we found a couple of literature reports that suggested that peroxide, even at fairly low concentrations, is actually really good at preventing urea hydrolysis. And this is a study from a few years back that shows that when you incubate urea with a certain concentration of hydrogen peroxide, even at very low concentrations, you're talking here about 30 millimolar, less than that. So this is substantially low concentrations of hydrogen peroxide than typically what you can purchase to use. And so what we found from these studies is that it is actually really excellent at preventing urea hydrolysis. And so we kind of went in with the idea that maybe we can work on something that does produce peroxide that will actually be able to help stabilize urine. And so the idea we came up with was, could we have an electrochemical cell that could be at a building scale used to be able to prevent urea hydrolysis from occurring? And the idea is that instead of having to store high concentrations of concentrated hazardous chemicals, could be acids, could be bases, could be even high concentrations of hydrogen peroxide that you would otherwise have to store. Rather than that, could we actually produce it on site? Could we use electricity in the real time to produce the right exact amount of hydrogen peroxide that is going to be needed to stabilize the urea that is coming in the collected fresh urine? And so the idea is, could we feed urine that is collected at a building scale to an electrochemical cell that is housed at that building, where we would use the oxygen reduction reaction? So electrochemically, you can reduce oxygen on carbon-based electrodes to produce hydrogen peroxide. So you go from oxygen to hydrogen peroxide. In a typical fuel cell, this is done on precious metal catalysts to produce water. But when you replace those precious metal catalysts, electrocatalysts, with carbon only, you can actually get production of urea in situ. And so the idea is, could we feed freshly collected urine into the cathode chamber, which is where we do the oxygen reduction reaction to hydrogen peroxide? Could we do that and help stabilize urea so that the effluent from that is going to have substantial amounts of residual peroxide that will avoid not only urea hydrolysis, but maybe also lead to some pasteurization. Maybe we will get enough disinfection of the urine while feeding it to the cathode as well. And so this was our concept. We recently published our results that I'm going to talk about in ACS, ESNT engineering. So if you're interested in learning more about this, I definitely encourage you to find that paper, or if not, you can reach out to me as well. But the idea here was, could we show a proof of concept of this, right? And so what we did was we did experiments with these electrochemical cells. We call them gas diffusion half cells because we feed the urine specifically into the cathode chamber of these. We have a carbon cloth-based electrode that allows us to produce hydrogen peroxide in situ. A lot of the work that led to how we can produce hydrogen peroxide has also been published previously. And the idea was, can we show that you can stabilize urea in this? And so we did experiments with synthetic urine where we would add urea and then also add the urease enzyme, and then track what happens with urea as we go along with time of storage. And so the actual treatment step is fairly short. So we just feed synthetic urine into these electrochemical cells for retention times of half an hour up to 4 hours of time. And then what we do is that we store that synthetic urine after treatment in the cathode chamber of these electrochemical cells for about 30 days. And so shown here on the right are results related to ammonium production. And so we can track here that untreated synthetic urine, we can track all the way up to about 10,000 milligrams of ammonia nitrogen that we can measure, along with an increase in pH that occurs, which is the hallmark of hydrolysis. But when we pass the urine through the electrochemical cells, when we pass the synthetic urine through that, when we apply a current and that current gets translated to hydrogen peroxide that is produced, we see that there is no ammonium production, the pH stays fairly stable. And that also is very similar to a chemically added hydrogen peroxide control, which also led to stabilization. So the lack of formation of ammonium and the pH increase confirms that we did get urea stabilization by just passing the urine through this electrochemical cell for a given amount of time. And you could store it for a really long time. Not shown here is that we could actually store it for up to 3 to 4 months and not get any hydrolysis occur. And we actually also confirmed that with measuring urea concentrations as well. One of the things that we are curious about was, could we bump up peroxide concentrations by increasing the current that is passed? Because remember, this is the electrical current that we pass to the cathode is what gets converted to hydrogen peroxide. And what we found that equivalent to the amount of current that we passed, so increasing current, so increasing concentration of peroxide that we would produce within the urine, we get lower and lower ammonium concentrations. Now, all of these on this relative scale compared to the non-stabilized urine are substantially lower. And so one could argue that you could optimize the current density to not even be at the very high level. One of the outcomes of this was that because the reaction through which we produce hydrogen peroxide raises the pH, we actually had the effluent from these electrochemical cells, the synthetic urine effluent from these electrochemical cells, we had a higher pH, and equivalently increasing the current led to higher and higher pH. And that high pH stayed at a similar level for each of those current density treated urine samples. And so unlike an increase in pH from hydrolysis of urea, this increase in pH was actually from the production of hydrogen peroxide, which itself leads to increased pH. And so it was not from urea hydrolysis. So that's different than what we would see in traditional, urea hydrolysis, where you would see a pH increase. Here, the pH increase was from the actual electrochemical reaction. there is an implication of this pH increase though. So if the pH of the urine that is coming off of these electrochemical cells increases, whether or not you adjust the pH after treatment has an implication on how long the peroxide that was produced in the urine stays stable, right? So if you don't adjust the pH and the urine pH stays high, over time you see this degradation of peroxide within the urine as we store it, versus if we adjust the pH to neutral, we see peroxide stay stable in the urine. And so this has implications on storage and transport, how long you want to store and transport after treatment in the electrochemical cell. But it could also have implications on whether you want to keep residuals for further use, maybe to remove pharmaceuticals, maybe to remove other organics, and so on. And so depending on the use case scenario, you would either adjust or not adjust the pH after treatment in the electrochemical cell. We are also curious to see how much this would cost, right? So we are talking here about replacing storing chemical on site to be able to store, to be able to stabilize urine, to now adding in electricity to produce a chemical that will then stabilize the urine. And so we did calculations on different current densities that we apply, how much applied voltage we got to be able to get that current density, and how much electrical power that amounted to. And so of course, increasing the electrical current then increases the electrical power. But what we want to do was wanted to compare the cost of this electricity versus the actual cost of urea production, right? So the cost of this electricity on a per kilogram of urea that's going to be recovered is about 1.2 cents per kilogram of urea. And that's based on roughly, when we measure in all of these tests, we recover about 80% of the urea at the end of 30 days of storage. And that's the metric that we were using to get to this cost. Obviously, you would have to process the urine further. You may directly apply the urine after further treatment as nutrient. And so you could argue that this cost, could go up or down from here, but compared to the cost of industrial urea production, we are at an order of magnitude lower. And so that's really the idea here, is that we can recover urea or stabilize at least urea for use as nutrient at substantially lower costs than it actually takes to produce urea. And so to sort of sum up what we found, we think that urea stabilization in synthetic urine, at least here, was possible. We are trying to scale this up to where we will use in our university building a system that will allow to treat real urine and show stabilization of real urine through in situ electrosynthesized hydrogen peroxide. It's very important to understand that when the urine is stored after treatment in the electrochemical cell, there will be an increase in pH, but that's not from urea hydrolysis. That's from production of hydrogen peroxide. And whether or not you adjust the pH has implications on how long you might be able to store it and transport it. And then finally, overall, we think this is an overall promising technology with very low energy requirements, ease of handling, because then you don't have to store high concentrations of chemicals at a building scale. And our next step is to really scale this up and show that it also works with real urine as well. And so with that, I'm going to end my presentation, and I look forward to the questions at the end of this session. Thank you.
Thank you, Sudeep. That's super exciting and really really interesting work. Exciting to see. I'll be excited to see how it works with real urine. All right, our next presentation is going to be from Philipp Markus. Going to be presenting about successful application of nitration and anammox to undiluted source separated urine. Philipp Markus is an environmental engineer working at AVOG in Switzerland as a research assistant. Since 2019, he has been working on urine treatment processes for efficient nutrient recovery. So welcome. And
all right, so I also try to be quick. I'm going to present about the successful application of PNA on urine, as you already said. It's a project funded by Melissa, the microecological life support system alternative of the European Space Agency. And we also worked in cooperation with the University of Antwerp. The research motivation for the ESA is that when they have space shuttles that will maybe in the future go to Mars, they need to deal with pressure losses from the cabin, and they need to get N2 gas to balance these nitrogen losses from the crew members. So they want to convert nitrogen in urine into N2 gas, and this is exactly what partial nitritation anammox process can do. There is also an application on Earth, maybe for some situations in which nitrogen recovery from urine for fertilizer production is not desired, but an efficient option for nitrogen elimination. And in this case, decentralized urine treatment with a PNA may be cost saving, as you all know that 80% of nitrogen is contained in urine, which only accounts for 1% of the conventional centralized treated wastewater flow. I want to give you a quick insight into the process, what it is about. Here you can see a simplified version of the nitrogen cycle where N2 is assimilated to ammonia, and then ammonia degraded to nitrite, and we are the conventional nitrification, denitrification into nitrate and N2 gas again. And now the anammox process can directly convert nitrite into ammonia, nitrite and ammonia into N2 gas. So it is a bit more efficient as it does not need the oxygen required for conversion of nitrite into nitrate. And more important for urine, that you do not need organics for denitrification, because in urine, not enough organics are contained to do it via this way. However, there are also some drawbacks. It is a very sensitive process, prone to nitrite accumulation, as AOBs can grow much faster than the anammox. As the anammox grow very slowly, the washout of bacteria can happen very easily, and the loss of biomass was a big challenge for establishing PNA on urine in the past years. So my research goal was to progress in the establishment on PNA on urine and to determine the reasons for the process instabilities that have occurred in the past. So this year we were finally able to establish PNA on urine successfully. So solution was the change from suspended active sludge flocks to biofilm growing on biocarriers. With this, we could maintain enough biomass in the system. So I'm going to present you the comparison of the two forms of biomass in the same reactor setup, which you can see here. And I was using a 12 liters reactor, which had online sensors of pH, O2, temperature, and fill level, which were also controlled, as you can see here in this table. And I was taking samples from the influent and the effluent for the nitrogen species and reference ions like potassium, chlorine, and sodium, and organics. And I was also taking samples in the reactor for the VSS and the effluent to balance the biomass. I was operating the reactor in fed batch operation. So I had a pH dependent feed until the maximum fill level was reached. And during this reaction period, aeration was switched on and off, as AOBs, the ammonia oxidizing bacteria, need oxygen, and the anammox are strictly aerobic. After this, we switched into a stirring phase to degrade any nitrite that may have accumulated, as we do not want to have it in the effluent, followed by a sedimentation phase to let the biomass settle before the effluent is then withdrawn and the cycle starts all over again. So here on this slide, you can see the elimination efficiency for both systems, the biocarrier system in red and the flock system in blue. And the flock system shows a very quick and strong decrease within the first days and weeks, whereas the biocarrier system could maintain a high elimination efficiency over the whole course of the experiment. And this was also reflected in the nitrogen elimination rate, which you can see here on this axis in milligrams of nitrogen per liter and day, where the flock system is showing a very strong decrease of the elimination rate almost until 0.
we have a peak here again, but this is not reflecting anammox activity. This is only reflecting ammonia oxidizing bacteria activity. So we had a strong nitrite accumulation here. Whereas the biocarrier system performed completely different. We have a very strong increase in the nitrogen elimination rate up to 800 milligrams of nitrogen per day over a period of more than 2 months, equal to more than 6 HRTs. I need to say I was pushing the reactor, accelerating the reactor by increasing the oxygen supply, and this may have also led then to a breakdown in the end. So we are actually confident that we would have also been able to maintain this stable rate of around maybe 400. Yeah. So now knowing that the biocarrier system works, we still wonder why does it not work with flocs? And we do not have a final answer to this, but we have some hints. Here you can see a floc picture of the inoculum, where you see a high density of flocs and also some granules. And already after 1 HRT with urine, you can see that the density decreases quite strongly. Yeah, almost no granules anymore. So we can say that flocs disaggregate when they phase urine and that they're washed out. And we are pretty sure that it's related to the high salinity in urine, but we are not able to make any further conclusions for the moment. So the take-home message is that the form of biomass is crucial for the establishment of PNA on urine, and that the biofilm growing on biocarriers allows for a stable process, whereas the flocs disaggregate and face quick washout. Thank you very much, and I will read through your questions.
Thanks so much. Really appreciate it, and exciting to think about uses for urine beyond planet Earth. So our last presentation in this, oh, okie doke. I'm being told we're going to move Dyllon's presentation to the next session. So we're going to do 10 minutes for questions now, and then we'll start the next session with Dyllon Randall, and then the rest of those. So we'll take questions now. And the first question we have is for Michel. What is the final form of the product that you're harvesting from the dryer, and how do you envision it being emptied and used or sold from the Autarky system?
Very good questions. I didn't mention that explicitly. The final product will be a dry product, and the trays from the evaporation reactor can be slided out, and then you can take off the dry product, and then the second product, the calcium-rich, the calcium phosphate-rich product, you can just draw at the bottom from the stabilization reactor.
Right.
And the idea is then to further produce, like we could imagine doing like a pelletizing of the product to be better marketable and sell it afterwards. But that's a further process step we haven't included yet.
Neat. Yeah, that's great. Thanks for the answer to that. We have a question for Kai Udert. Why did you decide to stabilize the urine with calcium hydroxide instead of using acidification?
Okay, I'm happy to answer that. Maybe that will be a question for Michel as well.
Mm-hmm.
Any case, the thing is with calcium hydroxide has a limited solubility. So when you add 1 liter of urine, only 5 grams of calcium hydroxide actually dissolve. So you don't need any active dosage. While with acid, you need active dosage. So you need to dose the exact amount. The other thing is you need quite a lot of acid, and depending on what kind of acid you use, it can also be dangerous to handle.
Right. Yeah. Thank you for that answer. This for one for Abe here. Abe, maybe you can just come over here. So the question for Abe is, what was the energy demand for the pasteurization step?
we'll just hop back and forth here. So our current pasteurizer is about 15 watt-hours per liter for pasteurization, but that's strictly determined by the efficiency of the heat exchanger. So if we use a more efficient heat exchanger, we could bring that number down as well. And I think that probably is a good idea, given that that number is about the same as we're predicting for the energy to concentrate. The other factor is that we may be able to pasteurize after we concentrate, in which case we would only be pasteurizing 1/6 of the volume of urine collected.
Great. Thanks for that, Abe. Next question is also for Kai. It says, are there urine treatments being developed that you have heard of since 2019? And what seems the most promising? And are there specific research areas that you think need more focus?
I think we have seen it here. I think the presentation by Abe, I think this is a really promising process. All the other presentations as well. I mean, what Michel presented, and actually Prithvi has developed a really similar process in Sweden. So I think this is really promising. Or, there are like very specific process steps like this hydrogen peroxide formation. I think there's really a lot going on. Maybe something which was not presented here, that's the production of a base with a microbial electrolysis cell, and at the same time an acid which can be used to rinse the pipes. This is something being done at the University of Ghent. Actually, there's really a lot going on at the moment.
Yeah, it certainly seems like there's a lot of exciting things. And I feel lucky that we've gotten to hear about a number of them today.
Maybe just one more.
Yes.
One more comment. Actually, what the work that Dyllon is doing, Randall, in South Africa by recovering urea or recovering calcium carbonate from urine, is also another aspect which is kind of new, basically.
Yeah, and we'll get to hear about that very soon, I think. Another question for Philipp and Kai. Do you foresee and will work on? Not sure that. Okay. So, what will work on a decentralized PNA system for household applications at building or community scale in the future? Or what do you foresee will work with regards to that system?
Yeah, I can try to answer. So it's a rather new finding that it actually now works. So this was from June to end of September. So before we were actually not even sure if we can establish this process. And therefore, we, for the moment, haven't made any plans for household application, as it's maybe also a bit too early for these thoughts. But yeah, maybe not. Yeah, maybe yes.
Yeah.
Maybe Kai has some more thoughts on that.
Maybe a very quick answer. I think with this biofilm system, which actually Philipp developed, I can imagine that this could be used actually on a household scale. And if you imagine a space mission, I mean, this is even smaller than a household, or in the same range as a household. So maybe this whole space research might lead to a really to a process that could be applied in a household.
Awesome. Well, thank you for that. I think we're going to do one more question, and then we're going to take a 10-minute break from wherever we end, and then we'll come back and we'll start with Dyllon Randall's presentation. But our last question for this one, is actually from Dyllon Randall for Abe. Abe, while the NPK nutrient ratio stays the same, do the other components in the urine change? Do you get precipitation occurring? Things like calcium carbonate when the temperature drops, since the solubility is very low for some compounds in urine? And what is the purity of the melted ice? Oh, Abe is saying he just answered that one in the chat. So I guess we can all look at the.
His presentation is recovering urea crystals from stabilized human urine. And Dyllon Randall is a chemical engineer by training and is currently an associate professor in water quality engineering and environmental sustainability at the University of Cape Town in South Africa. He heads up the research group focusing on resource recovery from human urine.
I'm going to talk about recovering urea crystals from stabilized human urine. So this work has been published in the Chemical Engineering Journal Advances. So if you want to read more about the details, you're welcome to download it. I'm going to begin by talking about the Haber-Bosch process. So this process takes nitrogen from the air with hydrogen from natural gas to produce ammonia, and then this is converted into urea. It is said that this process, which was developed in the early 1900s, is the key reason we have seen a significant increase in our population growth. It also consumes between 1 to 2% of the world's energy demand. So we wanted to see if we could recover the nitrogen in the form of urea that's present in human urine as an alternative to this process. So about 90% of the nitrogen in urine is fixed as urea. Now this urea degrades in the presence of an enzyme called Urease and produces CO2, ammonia, or ammonium, depending on the pH of the solution. Now this reaction can be prevented by operating at a low pH or a high pH. And we can achieve a high pH by essentially dosing fresh urine with calcium hydroxide. So what this graph shows us is that if we were to add calcium hydroxide to urine at a relatively low temperature, so below 40 degrees, we would ensure that we have a high pH and hence we prevent the breakdown of urea. This allows us to develop a passive dosing system. So in a container, we can add calcium hydroxide, to which we add urine, and then some of the calcium hydroxide dissolves. We add a little more urine and a little more calcium hydroxide dissolves. Provided we have enough calcium hydroxide, we maintain a high pH and hence we prevent that reaction from occurring. So this allows us then to collect urine, but also to stabilize it on site. And as a byproduct, we can produce a solid calcium phosphate fertilizer. And we produce about 270 grams of fertilizer per urinal. It is the liquid component that is remaining that we after though. So to take this forward, we have to consider the solubility. So the solubility of urea in water is substantially high, about 1,200 grams per liter. In contrast, the urea that's found in ethanol, or the solubility, is substantially less, at about 45 grams per liter. And as a comparison, the concentration range for urea in human urine is up to about 23 grams. So all the urea would theoretically dissolve. Something else to consider is the amount of other inorganic material that would be present in urine if you remove all the water. So these are some of the typical components, and you see their solubility in water. In contrast, though, the solubility in ethanol is negligible. So we can exploit these to purify the urea crystals. So the method we followed was as follows. We would collect the urine from our urinals, and then we filter it to remove the solid calcium phosphate and the liquid component. Then we evaporate all the water off to produce a dry product. This dry product is then dissolved in ethanol and filtered to remove any impurities that didn't dissolve. And then we remove all the ethanol to produce relatively pure urea crystals. But before we began, we had to accurately have the solubility of urea for a wide range of temperatures. So we conducted experiments and also modeled the system. And what we want to see is basically how this influences for urine. And what this graph shows is that the dashed line is the solubility of urea just in ethanol, and while the colored curves are for different urine compositions. And what we see here is that the urea in ethanol is a little higher when we have urine as a solution. And so we use this as a design spec where we have a solubility of 50 grams per liter at 22 degrees. So then we evaporated all the water off and then followed the same procedure, and we tested different types of urine. One was inorganic synthetic urine, then organic synthetic urine, and then human urine. And what we see from this graph is that the yield decreases when we follow the ethanol step, but the purity substantially increases when we treat the recovered dry product with an ethanol crystallization and purification step. What we also did, as I've mentioned, is we compared the solubility for different components or scenarios. So what the red curves show is just urea and ethanol, and then the yellow is basically our urine composition, and then the green is experimentally determined values for inorganic and organic. So what these results show is that when we have organic material, we actually have a higher solubility of urea and ethanol. The model we used, unfortunately, doesn't have these organic material, and hence we could not model the system. But going forward, this is the solubility that we should be focusing on in our design of experiments. We also wanted to look at how the purity might change when we increase the temperature. The thinking here was that perhaps at a higher temperature we would get purer products forming. And the answer to this was that actually the purity stays relatively constant regardless of the operating temperature. This is because the amount of impurities as well as the urea increases at pretty much the same rate, as you see by the blue and the yellow curves. We also conducted a theoretical mass balance where we treated 1 cube of stabilized urine per day. And from this process, we would recover 11.5 kgs of calcium phosphate per day, about 831 liters of water, and then 20.5 kgs of urea, which then could be used to produce liquid fertilizer as well as diesel engine fluid. The water that we recovered could be used to make these products. We could also recycle the ethanol and reuse it in the ethanol evaporation and purification step. Something else to consider is chemical urea hydrolysis. So while I explained how urea can degrade enzymatically in the presence of an enzyme, the urea can also degrade chemically simply by operating at a high temperature. So with this study, my Swedish colleagues showed that when we operate at excessively high temperatures, we actually lose a lot of our nitrogen or our urea because of chemical urea hydrolysis. So we would recommend that we don't have an evaporation step higher than 60 degrees, even though that this might speed up the evaporation process, because then you run the risk of using the very product you're wanting to recover. In terms of the energy estimation, so this is just based on a literature review. So one study found that to evaporate the water at 30 degrees requires about 30 kilowatts per meter cubed. And this is just for the water removal step and obviously doesn't include the ethanol step. But the ethanol step would theoretically be less because we would have less volume. So this study was based on a 95% water removal from dilute hydrolyzed urine. The other products that we could make would be a fertilizer, obviously, as well as plastics or resins, as well as diesel engine fluid, and even hydrazine, which is a key ingredient in jet fuel. But obviously you would have to get the purity substantially higher. So the next steps of the study are to test the process using more accurate solubility data, to fully characterize the organics that could form during the process and how they dissolve in the ethanol evaporation step, and then to also test different operating temperatures and see how that actually influences the process, and then also to test different solvents because we only looked at ethanol. Thank you. Any questions?
Our next person up is Stephanie McCartney, who will be talking about advancing membrane technologies for phosphorus and nitrogen recovery from human urine. Stephanie McCartney is a fifth-year PhD student at Columbia University's Department of Earth and Environmental Engineering, working in Dr. Nagai Yin Yip's group. Stephanie's focus is on nutrient recovery from human urine using membrane technologies. Upon graduation, expected in 2023, Stephanie plans to work in the wastewater treatment industry and is seeking opportunities. So you are all on alert. So Stephanie, if you want to take it from here, it's yours.
So I'll be discussing advancing membrane technologies for phosphorus and nitrogen recovery from human urine. So at this conference, we're all motivated by the aim to reclaim resources from diverted human urine in a circular economy model. So the focus of this work that I'll be discussing is on phosphorus and nitrogen recovery from urine to supplement conventional methods for synthetic fertilizer production, while at the same time decreasing nutrient loadings in wastewater and discharges to aquatic environments. So the goal of our work is to utilize membranes to selectively pass nutrients while retaining the other constituents and contaminants in urine, such as pharmaceuticals, pathogens, and endocrine disrupting compounds. Some of the contaminants that other researchers have discussed lead to social stigma. So the separation of specific forms of the nitrogen and phosphorus present in urine can be leveraged using membranes. So phosphorus is present as an anionic orthophosphate in both fresh and hydrolyzed urine. So this opens opportunities for the use of ion exchange membrane techniques to capture this phosphate. Nitrogen is present as ammonia in hydrolyzed urine. So this is a volatile form of nitrogen. So this opens opportunities to apply membrane techniques that drive volatile species across the membrane. So I will be discussing two techniques in depth, starting with phosphate separation and recovery using ion exchange techniques. So one ion exchange membrane technique is Donan dialysis, where an electrochemical potential gradient across an ion exchange membrane drives the exchange of anions across the membrane while cations and the other constituents are retained. Phosphate in the urine feed solution can exchange with chloride provided in a receiver solution where the product is ultimately captured. So one advantage of the technique is that it does not require an external electric potential gradient, but rather the electrochemical potential gradient is set up by ion concentrations in each stream, primarily a high chloride concentration in the receiver solution, which can be supplied via seawater, desalination brine, water softening regenerate rinse, or other low cost and waste resources. So we first wanted to explore the exchange of phosphate and chloride across an ion exchange membrane using a simplified recipe for synthetic fresh urine containing just sodium phosphate salts, and then simulated seawater receiver solution. So phosphate and chloride do in fact exchange across the anion exchange membrane. As you can see, the phosphate concentration in the receiver increases over time, and the chloride concentration in the feed increases over time, as well as the phosphate concentration in the feed decreasing over time. Importantly, after 3 hours of operation, the concentration of phosphate in the receiver is higher than that of the feed, yet the phosphate transport continues past this point, achieving uphill transport and 73% phosphate recovery after 6 hours of operation. However, in the previous figure, we used a simplified urine solution to demonstrate the phosphate and chloride exchange. So in reality, urine contains other anions of sulfate and chloride, and then bicarbonate if the urine is hydrolyzed. So these anions are also free to exchange with the chloride in the receiver solution, and this will influence the phosphate transport and selectivity. So these experiments demonstrate anion flux in Donan dialysis with different feed solutions. So for the non-membrane folks, flux is a key performance metrics that indicates the rate of an ion transport and recovery. For our purposes, we desire a high phosphate flux with minimal flux of other components. So the reduction in phosphate flux relative to the simplified solution is highlighted, so 90 and 97%, so it's pretty significant. So these additional anions in urine, particularly the high concentration of bicarbonate if we're applying hydrolyzed urine, pose competition for the exchange of chloride in the receiver solution, which really limits phosphate transport and ultimately reduces the purity of the phosphate in the recovered stream. So we need methods to combat this competing ion transport. Furthermore, it's quite obvious from this figure that we want to target fresh rather than hydrolyzed urine for phosphate recovery to avoid this significant bicarbonate flux. So flux and selectivity, here defined just as the relative flux of phosphate to sulfate, are pictured for two different membrane operations. So to enhance the selectivity, we introduced a monovalent ion perm selective membrane, which is the ASVN membrane, while the AMV is the conventional membrane. So the purpose of this membrane was to selectively target dihydrogen phosphate, which is the dominant phosphate species in our fresh urine, over that of the anionic sulfate. So this does in fact happen, as you can see in the figures. There is a higher selectivity for phosphate in the case with the monovalent ion perm selective membrane. However, this improvement in selectivity is at the cost of reduced flux relative to the conventional case. And this is because the monovalent ion perm selective membrane has a layer that adds resistance for transport. So in the future, we plan to explore other potential levers to enhance phosphate flux and selectivity. So one lever is pH manipulation. Okay. So now I'm going to transition to talk about the nitrogen recovery technique. So the technique that I would be discussing is membrane distillation, which is a process where volatile species are driven across a hydrophobic microporous membrane, while the non-volatile species, including many contaminants in urine, are retained. So the flux of a volatile component is proportional to the difference in vapor pressure between the feed and collector streams. So for the purposes of ammonia recovery from urine, ammonia in the urine feed stream is able to vaporize, permeate across the pores of the membrane, and then condense in the collector stream as a product. So the conventional method for membrane distillation operation, which we call CMD, imposes a temperature differential. So the feed stream is warmed and the collector stream is cooled in order to promote this vapor pressure gradient. So ammonia is able to permeate due to this driving force of a vapor pressure gradient. However, there's also water in urine, and due to this vapor pressure differential across the membrane, water is also driven to permeate. Now, this is undesirable because water permeation dilutes the product in the collector stream, and it also incurs energy costs to support the enthalpy of vaporization. So to combat this, we introduce isothermal membrane distillation, or IMD, where the feed and collector streams operate at equal temperatures. The lack of a temperature gradient minimizes the driving force for water permeation, and thus we should see less water flux across the membrane. However, there still exists a driving force for ammonia permeation. There still exists a vapor pressure differential in the same manner as the CMD case. Furthermore, the collector stream can be acidic and sourced from a waste stream, such as waste pickling brine containing acetic acid, to protonate ammonia that transports over to ammonium to avoid a buildup of collector side ammonia vapor pressure over time to enable this driving force for ammonia permeation to subsist. So this figure presents the performance in terms of ammonia and water flux. So ammonia flux is in green, water flux is in blue under all the different operations. So the IMDAC method achieves a higher ammonia flux and a suppressed water flux compared to the conventional case, which is the desired performance. The water flux is markedly suppressed because there's no imposed temperature differential on IMD, meaning that there is suppressed vapor pressure gradient. And then the ammonia flux is enhanced with the use of an acidic collector relative to a neutral pH collector. And we believe that ammonia dissolution into a neutral or high pH limits the ammonia vapor transport, and then this kinetic limitation is alleviated using a lower pH collector. And this is something we plan to explore further in the future. So next, we wanted to examine the energetic implications of the membrane distillation technique. So this shows the conventional versus the isothermal case relative to some circular economy model Haber-Bosch and nitrification denitrification. So this shows the energy needed to support the vaporization of the different components. So basically, as you can see, significant energy savings are achieved through preventing this water permeation and potentially at a competitive level with the circular economy approach. Just to bring the research back into perspective, we all want to achieve this circular nutrient economy. It's crucial to protect aquatic environments and to produce sufficient fertilizer for growing populations. So the idea of this work is to develop nitrogen and phosphorus recovery techniques that are able to leverage on some of these waste resources, waste heat, waste chemical streams, and other non-toxic chemical streams to produce fertilizer from urine. So the next steps are to explore other possible lever points, such as pH manipulation, to further enhance the performance for Dyllon dialysis and membrane distillation. So I want to thank my lab group and Dr. Yip, and please let me know if you have any questions in the chat and after in our discussion. Thank you.
Wonderful. Thank you very much, Stephanie. I could comment on all of these by saying the same thing. It's so fascinating, all the different ways to approach these same questions of resource recovery and energy use minimization. I think it's wonderful that we're all applying ourselves to these in so many disparate methods. We have another method coming up from Courtney. Her presentation is concentrating stabilized human urine using reverse osmosis to produce fertilizer. Courtney is a PhD candidate at the University of Cape Town, supervised by Associate Professor Dyllon Randall. Her research focuses on using pressure-driven membrane separation processes to concentrate urine to produce a concentrated liquid fertilizer. Her research group's core focus is to valorize urine through resource recovery. So let's head back to South Africa, and Caitlin, you have the floor.
Hi everyone, my name is Caitlin. I am a PhD candidate at the University of Cape Town, and today I'll be presenting our findings on concentrating calcium hydroxide stabilized urine with reverse osmosis, specifically focusing on the effectivity of different pretreatment methods to prevent membrane scaling. This research is a summary of the following papers, which are in various stages of publication. I'm sure everyone here is well versed on the potential urine has to be used as a more sustainable fertilizer due to its high NPK content. Methods for source separation are well established, and urine-derived fertilizers have been proven to be effective. So why don't we see urine fertilizers in every garden center? Because urine is 97% water, it's expensive to transport. So, the gap in the process is to maximize the recovery of nutrients from urine in a smaller volume, for which each presenter here today has a solution to said problem, with each solution having its own pros and cons. Our chosen method of concentration is pressure-driven membrane processes, or reverse osmosis. Why RO? This is a well-established technology. It accounts for 44% of global seawater desalination. The process is therefore commercially scalable, and it's modular, so it's simple to increase capacity. And at scale, it has a lower energy consumption compared to other concentration technologies. A comment we often receive is, but RO is so expensive. If water is your product, such as with seawater desalination, then yes. Bulk water can only be sold for approximately $10 per cubic meter, and the brine still requires disposal. In our process, the brine is the product. Niche liquid fertilizers can be sold for as much as $1.57 per liter, which is significantly more valuable, and water is an additional useful byproduct. With a large-scale treatment process, the time between collection and treatment could be a couple of days. Therefore, to maximize nitrogen recovery, urine should be stabilized to prevent urea hydrolysis and subsequent ammonia volatilization. Our preferred method is calcium hydroxide addition, for the reasons previously mentioned by my supervisor, Dyllon Randall. The downside with this method is that urine is then saturated with calcium hydroxide, so when you begin to concentrate it, the calcium hydroxide immediately precipitates, and the membranes begin to scale, looking something like this. For concentration of urine, using RO to be feasible, we would need a method to prevent this scaling. Whilst there are many commercial anti-scalants available, their effectivity is limited for feeds with high saturation indices, such as urine concentrated with calcium hydroxide. We therefore needed to find a pretreatment method that removed the scaling ion from the feed altogether. Our hypothesis was that if a carbonate ion was added to the system, this would react with the calcium to form calcium carbonate. Because calcium carbonate is extremely insoluble, it would precipitate and could then be removed with filtration. We investigated two methods to do this: air or CO2 bubbling and adding a bicarbonate salt. Our key findings were, for air and CO2 bubbling, that the rate of CO2 addition needed to be carefully controlled to ensure precipitation rate was faster than the decrease in pH, and that although CO2 bubbling is quicker than air bubbling, it is expensive and does not have the added benefit of sequestering CO2 from the atmosphere. With the bicarbonate salts, we found that any carbonate or bicarbonate salt effectively reduces the calcium concentration, and that the choice of preferred salt would be based on the cost and the additional cation added. Both sodium and ammonium bicarbonate were promising. The next step was to test the effectivity of these pretreatment methods in reducing scaling of the RO membranes. The other challenge is urea. Because it's a small and uncharged compound, it makes it difficult to reject in membrane processes. Current papers assessing urea rejection in urine are limited to nanofiltration and low-pressure RO membranes. We specifically wanted to look at a higher operating pressure as well as a seawater RO membrane to see if this could improve the urea rejection and therefore its recovery in the brine. In 2006, Eck and colleagues did look into seawater RO membranes. However, they were treating hydrolyzed urine, and ammonia and urea have very different rejection properties. Our methodology included using synthetic urine to ensure a consistent composition throughout all the pretreatment experiments, and then, once a preferred pretreatment method had been chosen, we repeated the experiments with real urine. Stabilized urine was either not pretreated or pretreated with air bubbling, ammonium bicarbonate, or sodium bicarbonate addition. The urine was then concentrated with a lab-scale RO system using a seawater RO membrane at 55 bars. The permeate was collected and the brine line was recycled to the tank. Measurements were taken at different water recoveries, and the experiment was ended at a water recovery of 60%. This was based on a combination of time and equipment limitations. Our key findings. As the urine is concentrated, we expect to see a decline in flux. However, without pretreatment, we see a much steeper flux decline caused by the membrane scaling. All the pretreatment methods showed improved flux, urea, and ion rejection compared to untreated urine. Each pretreatment method resulted in a different feed pH, which we believe to affect the urea rejection. We plotted the urea rejection as a function of solution pH based on the methods used, and we saw a direct correlation. Since urea is the most difficult to reject, we used this as a decider of the best pretreatment option, determining that air bubbling was the best. Whilst the difference in urea rejection with air bubbling or ammonia bicarbonate addition is minimal, and adding ammonium bicarbonate is much quicker, we felt that air bubbling was the better option because it sequesters CO2 from the atmosphere and adds no additional ions. Dosing a salt also requires the production of said salt and all the greenhouse gas emissions that go along with that process. We then compared real urine stabilized with calcium hydroxide and pretreated with air bubbling to synthetic urine. In terms of permeate flux and analysis of the membrane surface, we didn't observe any significant differences. However, these were short experiments and the effect of continuous operation on the flux should still be checked. The most interesting observation was an increase in ion rejection, specifically urea. Rejection increased by approximately 8% at 60% water removal. This results in increased urea recovery from 79 to 85.5%. In 2006, Pronk and Associates observed a similar phenomenon with nanofiltration of real and synthetic urine. They hypothesized that this could be due to the formation of organic matrices that essentially increase the size of urea, making it easier to reject. There are two factors that may have been limiting the progression of urine concentration with reverse osmosis. Firstly, the potential for membrane scaling. In this study, we showed that an air bubbling pretreatment step reduced the potential for this to happen. Secondly was low urea recovery. A comparison of urea rejection from other studies using low pressure RO membranes and loose and tight nanofiltration membranes shows that using a high pressure seawater RO membrane improved the urea rejection significantly. Due to the high salt content of urine, and therefore its high osmotic pressure, you might be thinking that water recovery will be limited to, say, 50 or 60%, such as with seawater desalination plants. However, there have been new membranes developed that can operate at pressures as high as 120 bar that could potentially overcome this problem and increase the water recovery further to what was even achieved in this study. We advise that these also be tested to determine how they affect urea recovery and scaling. So what is our vision for the future? Well, different treatment options work at different scales. A process like this would obviously not be feasible on a household toilet level, and instead you might have, say, an evaporation setup. However, we envision this process being implemented where urine can be collected on a large scale, such as, say, airports, shopping centers, or festivals. The urine would then be concentrated in an on-site treatment facility. The fertilizer product would be sold, and the water could be recycled within the building for non-potable uses, thus bringing us one step closer to closing the loop on resource recovery. Thank you.
We're going to switch gears now and look, instead of at urine treatment, we're going to look at an innovative source separating mobile toilet. The presenter is Thor Retzlaff. The title is Wasted Development, Separate Waste, Connect Communities. Thor is a passionate entrepreneur, skilled storyteller, and avid mountaineer. He's the founder of Wasted Development, as well as the nonprofit organization Do Good Shit. Since founding the nonprofit in 2018, he has orchestrated urine diverting toilet installations in Chile, Argentina, and the United States and Nepal. For the past year, the Wasted Development team has integrated source separation technology into portable toilets, and they look to position themselves as a collaborating force for source raw byproducts. Thor, you have the floor.
All right. Hello, everyone. Can you hear me? See my screen?
Yes. We hear you when we see your screen.
Awesome. Thank you so much, Team Rich Earth, and everyone attending today. My name is Thor Retzlaff. I am the founder of Wasted, along with other two incredible co-founders, Brophy and Taylor. You can see in this image here. And I'm going to tell you a story today about how we are positioned to support the tech research that everyone has done such a good job explaining the past 2 days, and will do so tomorrow. But before I get into it, I have to say that last year when I attended the Rich Earth Summit, it completely changed my life, actually. It was pretty wild being able to engage with these experts in the field and walk away with an understanding that our nutrients are valuable. And that paired really well with my sanitation journey. And that's what I'm talking to you about today. So back in 2018, we were on the side of Mount Everest, and we came face to face with 26,000 pounds of human waste left in these open pits in Gork Shep every single climbing season. And that was kind of shocking for us. So we decided to set out and figure out a solution for that. We didn't even know where to start, but we took this idea and we put it in the form of a nonprofit, and that's Do Good Shit. And our mission is to reduce the harmful impacts of human waste on the environment and the surrounding communities. So as we kind of got to work and tried to figure out what does this look like, we did this tour. We called it the toilet tour, where and I got in a car and we drove all around the Pacific Northwest, taking apart toilets. And it was the most humbling work we've ever done, but it was really informative to understand how do we properly manage sanitation, specifically in these sensitive environments like Camp Muir or Summerland Trail or Hot Springs. And so the core thesis we kind of walked away with was urine diversion makes it a lot easier to manage our waste. And then when you pair that with ecological sanitation practices and the processes that we've all been discussing for the past 2 days, then an opportunity arose. And that is to build a portable source separation toilet that requires no behavior change. In other words, what waste development is doing is we are reinventing the porta potty. And for most people we talk to, it's arguable that the porta potty right now is one of the worst public facing interfaces that we have to use. And so we're going to go and completely kind of flip that on its head. And so kind of what's guiding us towards this vision is, how can we create this product, this piece of hardware that integrates into the existing landscape? And so with source separation in mind, we thought, okay, well, what does it look like right now? How are we moving around these products? And then taking a step back, it said, how are we actually going to separate this waste? And so a year ago, Taylor drew on a napkin. I know there's a lot going on the screen, but essentially drew on a napkin how we could separate waste with a simple mechanism that we call a trapdoor. In short, it's a sloped angle. The urine flows off with gravity, and you push the foot pedal, and it drops down into their respective containers. Once we said, hey, we think this can work, we took that into the lab, and we used fake poop and water, the urinator. We 3D printed the urinator, and started testing this. And while it wasn't the real thing, we knew that the real thing would come down the road. And so this was a really fun, informative process. The bench scale testing and trying to figure out, does the source separation work or not? And that eventually led us to our MVP. We said, let's go build a structure, a semi-portable structure, let it be known. This is like not that portable, but the core idea there was to test this source separation tech in the wild. We wanted real people, real strangers engaging with this toilet to see what they would say and if the technology worked. That being said, we made 5 of these alpha units, and we effectively deployed one of them in conjunction with the Rich Earth Institute in Vermont. So for the past 4 Saturdays, we've had our unit at the Brattleboro Farmers Market, having people use this and give us feedback around, did it work or not? What would you change, this and that? And so that was a really informative time for us. And at this point, we had around 500 users use our toilet. And for the most part, liquids ended up in our liquid container and solids ended up in the solid container. But there's a lot to be learned, right? And so there's a lot of product optimizations that are going into the next phase of what this looks like. But it was really exciting to get this MVP into the field and figure out, is this a possible path forward? And our hats go off to the Rich Earth Institute, especially Arthur, who has orchestrated their portable sanitation arm. And our goal really is to augment the aggregation of these waste streams and collect from not just standing people, but everyone. And that's really kind of leading the charge on why we built the wasted unit. Excuse me. Awesome. And so in this collaborative space, everyone, we've been talking about the more processing, reuse side of this. Our responsibility and the way we want to position wasted is in the diversion and collection processes of this entire ecosystem that we're all working together in amplifying and moving towards, grand adoption. And so while we focus the sourcing of our byproducts through the toilets, we aim to be deploying beautiful systems to aggregate these waste streams. And so the next phase of our MVP, this beta unit, is going to simplify the source separation tech and further optimize the actual unit to be deployed. With that being said, we want to essentially build a platform for R&D, supporting the tech research that is currently going on with the resources that we will be able to aggregate. All that being said, we're trying to make the blueprint of portable sanitation so that we can allow existing operators to adopt this technology and further source raw products to go into the circular sanitation economy. All that being said, really excited to be here. It's been really fun to be boots on the ground, working towards kind of the next steps, what we're doing. And leave you with a quote we heard from Julia, who's just brilliant with the puns. Be the change you wish to see in the world. And so if you're interested in learning more about our tech, or if you're interested in a collaboration or partnership of any kind, please do not hesitate to reach out. But again, I appreciate everyone taking their time to be here, and it's really informative. So.
Terrific. Thank you, Thor, for sharing your ambitious plan to bring source separation to the masses. Appreciate your presentation and everyone who has talked in this the second phase of the panel. We have had a lot of questions and answers coming through in the chat, and I believe that almost everything has been answered in the chat as well. We just have a couple of questions here. The one in bold.
Yeah.
Okay. A question from Kai to Lei, which was, how will you remove the pharmaceuticals later?
Sorry, I was muted. Thanks for the question. Yeah, so I think I just answered that to Michael, but like, yeah, we are actually currently investigating two possible routes for our basic scientific study. So the first route is that we are going to, because urine already contains a significant higher level of pharmaceuticals than other wastewaters. So we were now investigating like if this current level can already show some inhibitions and stabilization effect of urine. That is what we are undergoing right now. And the other things is like if we are going to use much higher concentration of the pharmaceuticals in the urine stabilization, we are going to, by the end of the treatment, to incorporate membranes or advanced oxidation process to eventually remove those micropollutants in the end.
Okay, thank you. And another question has come in for Thor as we were just talking. And that question is, do you have a price point you expect to sell these for, i.e. to porta potty companies?
Great question. We definitely took the unscalable approach out the gate building these units. But moving forward, the current competitive pricing in the space is anywhere from $1,000 to $2,000 per unit. And so I think that we are going to be aiming to hit that mark, probably on the lower side, around $1,000 to $1,200.
Great, thank you. And then we have a couple other questions that have not been answered. One of them is from Dyllon Randall about pharmaceuticals again for Lei, which was, what happens if people did not take these specific pharmaceuticals? The urea in the urine would not be stabilized?
Yeah, good question. So we actually, as you can see here, we presented the pharmaceuticals with the phenol groups and disulfide. Disulfide, the diaphragm is actually a very, I think it somehow controls the alcohol thing. Sorry, I forget how the word, but that is a very common drug that you can buy. And also the phenol group is a very common functional group in the pharmaceuticals. So we would imagine like there are going to be some level of that in the urea, but if not, as I mentioned, like we can also incorporate other wastewater with high concentration of the pharmaceutical. For example, from the hospital wastewater, we all know that phenol are very commonly used in the hospital as a disinfection, something like that. So again, this is only a very preliminary result from the basic scientific perspective, and we are trying really hard to make it more practical in the future uses. Yeah, thank you.
Thank you. A couple more questions for Thor have come in. One is for the separation mechanism. Did you partner up with EOS to integrate their urine trap, or did you develop your own system?
Great question. While we did not partner up with EOS, we utilized a lot of the existing research and knowledge on the internet to inform our design. But the actual mechanism we developed was, like I said, tailored on a napkin. So it's our own kind of tech that we've developed, and that was from that research, that toilet tour in the field, like figuring out how this works best. So no and yes.
Okay, and another one is it says, "Hi Thor, nice design. Maybe I missed it, but how and who was going to treat and collect the waste from the toilets?"
Great question. So that's actually what we're working on now. Since we've kind of validated the source separation tech, the next phase of our business development is building out the operational landscape of how can we create a company that can go operate within the existing portable sanitation market to source these resources. And the analogy I like to use is that the portable sanitation marketplace is already moving all this waste around, yet it's combined and has a bunch of blue goo in it, right? So we're gonna do the same thing, but separate it and bring it back to treatment facilities. So there is already a market there that pays to move the waste around. And so Wasted is going to create the operational landscape to do that.
Okay. And since your presentation just ended, I think your questions are all trickling in right now. We have a couple more. Do you have any of your prototypes available for use in other places?
Great question. Yeah, so our first alpha unit is right next to Abe in the Rich Earth Institute right now. We have 4 other alpha units that do not have homes yet. And so we are working towards figuring out the most strategic path forward in deploying those and getting more usage out of them. So please reach out if that's of interest.
Great. And it looks like the last question is what type of UD toilet shape did you use to avoid user mistakes, like putting paper in the wrong place and plugging up the urine pipe?
Good question. The way we designed the toilet is the user, no water is required. And so there's a singular hole. We actually didn't incorporate a urinal because we wanted to maximize the amount of waste going through our source separation mechanism. But there is only one hole. And because gravity's doing all the work to separate the liquids, if I might be misunderstanding the question, but it'd be hard to put something in the wrong place. And as long as you flush or use the foot pedal, then it will effectively divert both streams. Let me know if you need clarification there.
Okay. And there's another one now that is, what sort of clients are you looking for? Maybe the Olympic Discovery Trail, which is accessible by road.
Right now, I can't say. I think it's an open map. We're looking for conversations. Like if we have, I'm going to use a specific example of the Rich Earth. They already had an operation with Arthur where they're putting out retrofitted porta potties. We designed our alpha units to integrate seamlessly with the system that they already created, so that it was not a giant leap for them to adopt this tech. And so I think that we're open to any and all conversations. If we're able to deploy an alpha unit and figure out the back-end processing, then let's do it. But again, I think the next step there, if interested, is let's find a time to chat.
Okay, terrific. Well, that brings us to the end of our questions, and we're ending right at 1, which I think gives us 10 minutes as a break before the next session. So thank you to all the presenters in this session and the previous half of it. Great topics, great research. I think I've got a lot of rereading to do and a lot of reaching out. So thank you so much for sharing all this great knowledge.